Crash Course Instrumentation, Episode 6, Graphing Voltage, Current, and Circuit Behavior. Welcome back to Crash Course Instrumentation. In this episode, we're exploring how to visualize electrical behavior using graphs. Because sometimes the best way to understand what's happening in a circuit is to see it. We'll break down how voltage, current, and resistance appear when plotted over time or space, and how this helps us diagnose problems, monitor performance, and make better design choices in the real world. Let's start with a simple one. A voltage drop across a resistor. Imagine a wire running from the positive terminal of a battery through a resistor and back to the negative terminal. If you plot the voltage at different points along this path, you'd see a sudden drop as you pass through the resistor. Why does this matter? Because that voltage drop represents one energy being used up, transformed into heat, light, or motion. By looking at the graph, you can tell where the action is happening in the circuit. Now imagine plotting current versus time in that same circuit. If everything is working properly, you'd see a flat line, indicating a steady current. But if there's a problem, like a loose connection or a partial short, that graph would spike or dip. These variations help us see problems we might not catch with just a voltmeter. We can also plot voltage versus time. This is especially useful in circuits with AC power, pulsed signals, or digital logic. A DC power supply would show a flat line, constant voltage over time. But an AC signal? That graph would wave up and down, often in a smooth sine wave. A digital signal would look like a staircase, clean high and low transitions. Each of these graph shapes tells a different story about how energy is moving through the circuit. Let's take it further. If you plot voltage and current on the same graph, you can see how they relate. In resistive circuits, current and voltage rise and fall together. But in capacitive or inductive circuits, they shift out of sync, a concept called phase shift. This is critical in real systems. If voltage and current are out of phase, you can get energy loss, heat buildup, or even system instability. Visualizing the relationship between these signals helps techs tune systems, improve efficiency, and avoid failures. Another useful view is the power versus time graph. Since power equals voltage times current, P(V)(X1), plotting it shows how much energy is being consumed or delivered at every moment. Peaks in power might show startup surges or sudden loads, things you need to account for when designing or troubleshooting systems. These graphs don't just live in textbooks. They show up on oscilloscopes, data loggers, SCADA systems, and calibration tools everywhere. Learning how to interpret these visualizations is a major step in becoming a confident and capable instrument tech. Here's a real-world example. You're monitoring a flow transmitter powered by a 24V loop. Normally everything looks good. But then you see a slow dip in the voltage at the transmitter terminals over a few minutes. That might point to cable resistance increasing due to a loose screw terminal or a corroded wire. That voltage time graph is a warning sign, telling you something's going wrong before the signal fails. So let's recap what we learned today. Voltage and current can be visualized over time or space using graphs. Voltage drops show where energy is used. Current spikes or dips reveal system disturbances. Voltage and current plotted together help detect phase shifts and inefficiencies. Power plots reveal energy trends and load changes. Graphs are more than pictures. They'll be tools. Tools that give you insight, clarity, and an edge when analyzing, designing, or troubleshooting systems. Thanks for tuning in to Crash Course Instrumentation. In our next episode, we'll look at what happens when circuits go wrong. Faults, opens, shorts, and more. Don't forget to like, subscribe, and share with anyone learning how to see their circuits in action. See you next time.